Hello everyone, you must have heard about the OpenAI DALL-E neural network, which can create images from the human understandable text captions for a wide range of concepts. It means the DALL-E can create images by giving a text context in a variety of format, means paintings, means emojis, means natural setups and variety of images based on given context. This video is not about DALL-E, it is more about ruDALL-E, rudalle, which is an open source version of DALL-E created by a group of AI engineers from Russia. A few weeks back, I had an opportunity to use the ruDALL-E model and I was really impressed with its performance. So I decided to create this video so that I can tell more about this open source machine learning model to everyone. Hello again, my name is Avkash and our objective in this video is to understand not only ruDALL-E architecture as well as learn more about transformer neural networks. We will learn more about ruDALL-E neural networks along with the text to image generation pipeline. We will learn how a general or the DALL-E proposed image to text pipeline works and how the ruDALL-E text to image generation pipeline is different from DALL-E. Because they both DALL-E and ruDALL-E, they both are transformer neural networks. So we will learn the original proposed transformer neural network architecture just a little, and we are also going to look into the vision-based transformers also. We will learn how the ruDALL-E uses the same vision-based transformer architecture as used by DALL-E, but also uses other functionalities to complete the task of text-to-image generation. ruDALL-E has various versions of models, and some of these models are open source. So we are going to look into the various versions publicly available in the open source domain. At last, we will run the ruDALL-E open source model on Google Colab and generate images by passing some of the text by ourselves. We will use all three ruDALL-E models which are available in open source domain and see their results in real time. My objective from this video is to give you as much as information about ruDALL-E so that you can learn even more about DALL-E itself, and if you would want to create your own application to generate images from the text, you could use the ruDALL-E models. Not only that, if you would want to use those models to train and then extend for something else, you can definitely do it. So let's get ourselves started. So ruDALL-E is a text to image generator transformer. It's using the encoder and the decoder architecture, which is similar to other proposed transformer and exactly what the DALL-E is using. And there are two different versions of ruDALL-E. The XL model has about 1.3 billion parameters versus the XXL model is supposed to have 12.0 billion parameters. They both are text to image, and one big difference is that the ruDALL-E XL model is the open source. The XL model has three different model types, and then the very first model, which is the Malevich, that is what is trained with 120 million text image pairs. The second model from the XL family is the Emojich, and which is also XL, and it is trained with 120 million text image pairs plus 2749 text emoji pairs. So this model can be used to generate emojis. And finally, in the same XL family, the third model is the Surrealist, which is actually trained with same 120 million text image pairs plus 190 text image pairs of paintings. So using this Surrealist model, the painting style art can be generated with the text input. So we can take a quick look about what is the multimodal AI, because if you talk about DALL-E, or if you talk about the Vision Transformer or the original Transformer architecture, it was proposed for multimodal AI. So let's take a look the most common data types we are using with the task we are performing through AI. So we have image data, we have text data, and we also have the audio data. So the objective for us to take these data types and use the data specific encoder. With image data, we need an image encoder. With the text data, we need a text encoder. And finally, with the audio data, we need an audio encoder. Once we have encoders, these data will be encoded, and the encoded image, encoded text, and the encoded audio segments will be created. We call them sections for better term, because that is used. And now once we have our data ready, that can be fed to a training model, and that is the transformer model architecture, which is the base for the DALL-E, which is also the base for the BERT as well as the GPT and GPT-3 models. Model is ready, it means that we can take this data, combine all this data together, and finally fed into the training system. And I just wanted to make sure that please understand this is just a conceptual diagram. It does not happen like that way. One thing I wanted to inform that the DALL-E, the ruDALL-E, even GPT, BERT, they all designed for multimodal data types supporting images and the text data. These models, they do not support the audio yet. However, some open source groups who have created and made models available. So this audio clip model, which extend the clip CLIP transformer, which is designed by OpenAI, and it extends its support to also use audio as input. The next topic we need to give really good attention is to understand what is the image generation pipeline. It's a general pipeline design which is based on the DALL-E or the OpenAI theme framework. So we have input text, and this input text has been fed into the transformer. It could be vision and text transformer, and the images are generated. So if we look into the models available which can take the input data and convert that to images, we could see the DALL-E version 2 is not available, but the DALL-E is one of the model which is designed by OpenAI team, and the ruDALL-E, which we are just talking in this video. And there is also another model called Cogview. So these two models are open source, you can use them. At this point, we still need to validate whether the images which are generated are really correct as per the requested text. The next step, what happens is that the result ranking happens with a proposed design called CLIP. So CLIP is the another model which is proposed by OpenAI team. The input for role of CLIP transformer is to understand all the input images, understand the text required, and rank all of these images which are based on this given text. At the next step, the component such as super resolution can be used. It is optional component because at this point the results are already generated. The top end result, depending on what the clip transformer performed, and based on the performance result, the top end results are available. However, the quality resolution improvement can be added through super resolution component. Information about clip is available on this website. Let's take a look what happens with the ruDALL-E. So we already have the ruDALL-E, which uses the same transformer as the DALL-E, and based on the input text request, it generates the candidate images. In the next step, there is the ruClip, which is the ruDALL-E team created based on open source clip architecture, and that code is also available at this GitHub. So the ruClip component is what works together to understand the best or the top images based on request, and the final image block or image collection is generated. This image collection can be used by super resolution component, which is also the part of ruDALL-E, and using the super resolution, the selected images can be improved for higher resolution. In our GitHub examples, we are going to use the super resolution API and improve our result set. So you will be seeing the example of this. So here is the proposed architecture for the transformer. So this part of the transformer is the encoder, and that part of the transformer is the decoder. So here is the vision transformer, which is proposed by Google. If we would want to go a little more deeper to understand what happens in vision, here you could see that the input image has been split into the linear collection or linear sequence of patches, and that's where the linear embedding is. And then finally the class is added, and this is your encoder. So this image explains little more deeper about what happens inside the vision transformer. To try the ruDALL-E model by yourself, please visit to this website, and here you could try out like I did try this earlier. So it takes some time for your image to be generated, and I did ask exact same thing earlier, and this is what I have got back. So at this point, you have very good understanding about ruDALL-E architecture, the text to image generation pipeline, and the general purpose transformer architecture. I also believe that you have very good understanding about how the information is being synthesized and processed by the transformers for both images as well as the text. Now it's time for us to spend some time in code and look into how we could utilize the ruDALL-E open source model available at the Hugging Face or their own GitHub repo. So let's move to Google Colab now, and we will do rest of the work over there. Let's give a test to the ruDALL-E models. Here I am cloning the ruDALL-E GitHub repo, and just to make sure that I do have support for GPU, I just want to make sure that you also enable the GPU if it is not enabled in your Google Colab. Finally, I'm installing the ruDALL-E package. So after ruDALL-E package is installed, I will show you that when we cloned the ruDALL-E GitHub repo, we also got this requirement.txt. So we will see that there are a couple of other packages which we need to install. So I'm going to run pip install, and if there are any packages required for us to make it work, those packages will be installed. At this point, I just wanted to show you that these are the resources available in this local machine when I cloned the ruDALL-E repo. Let's import some of these methods from ruDALL-E, and as you could see that this function loads up the model which we want to request. This loads up the tokenizer. Here we have the variational autoencoder and also the real ESR GAN, and that is used to enhance the image quality. Then from the pipeline, generate image method, show results, and super resolution method. So this is the pipeline, and that is the importing the main core component. So let's import the pipeline. After that, because we want to use the GPU for our generate image function, so I'm just making a call to see that if the CUDA or the GPU is available in this Google Colab. So I will set up the device to use the CUDA 0, means the very first GPU. Next, we are going to create these three objects related to our generate image requirement. So first, tokenizer, which is going to call this get tokenizer, then DALL-E, and that is where the model we are going to import. So Malevich, which is the XL ruDALL-E XL model with 1.3 billion parameters. We are using the pretrained with support with floating point 16, and devices GPU, and finally VAE, variational autoencoder VAE. Okay, so these three objects will be created for us, and each one is important. Tokenizer is ready. The next step, we are downloading the model. The variational autoencoder is also ready. So all these three objects are ready for us. Now we are going to set up a text which will be used as input to generate images. This text is kind of very contradicting and little complex, so I will make it very simple first. So that's kind of positive sentence. So that's our text. So now the generate image method is being called from the ruDALL-E pipeline by passing the input text, tokenizer, which is this, DALL-E is our model, and we are using the Malevich model. And remember, there are three different models we have. So this is the first one, and by passing the top K variable, which is 1024, and the top and all the images which achieve the 99% result ranking, so they should be selected, and the total number of images we want 12. Actually we can use 6, even better. So let's run it. It's going to take some time. So the result set has the images here because we requested 6 images, so I will change this parameter to 6. So that's going to generate the 6 images, and there are the 6 images. So here we have ocean and ocean, but none of these images have the penguin in it, but at least we have got something coming out from it. We can also do not pass this 6, and that gives us the images. By default, this way it gives the 6 images in a row. If you would say that you want these images, and you could say I want these images 2 in a row, then you can pass this 2, and it's going to show you 2 images per row. If you will not pass, it's going to show you all the images here. Now if you would want to generate the high resolution images, then we could call this get real ESR GAN method by passing the type and the device, and that's going to give us an object. And now we could pass the result set images, and finally the object real ESR GAN, and that's going to give us the super resolution images collection, and then we can render that super resolution image collection to see the results. Now if you would want to use the same API to get a different model, so we could actually call a different model. At this point we will use the emoji model, so we could call emoji ch. That's the model, pre-trained, everything same, and we just call it DALL-E Emoji. So now we have got the DALL-E Emoji model, so we could use the same method which was used to generate, and here we just need to pass a new text and the new DALL-E model. So our DALL-E model is DALL-E Emoji. Here we need to pass the text here, so we could say funny book emoji. Pass the text, tokenizer, everything is okay, and we just call it DALL-E Emoji. Now we need to pass the text emoji. So the emojis are created. Let's take a look. We asked for 6 images and our objective was with funny book, and that is what has been generated. So the next model is the Surrealist model. So if we would want to use this model, we have to get newer methods from the ruDALL-E team. So first we need to clone this repo. The next step, we are setting the path and then importing this get ruDALL-E model. And now we could make this call to Surrealist model. So this is a Surrealist model. XL is going to be downloaded. After the model is downloaded, we need to set up the ruDALL-E aspect ratio. So here we have set up the aspect ratio with the model is being DALL-E. We already have the variational autoencoder, tokenizer, everything ready, devices CUDA. Now I'm using the Russian word with it. So let's run this. So we requested to generate 4 images of ratio aspect ratio 32:9. So let's see the images 2, 3, 4. If we say 1 image per column, so now we could see 1 image, 2 image, 3 image, 4th image. These images are created. If you would want to generate images which are based on 9:32 means vertical images, we could actually set the vertical. So we could say we want AR, we just call it 9:32. So let's use the 9:32. That's new aspect ratio. Use this new images object. So we just call it new, and here we could use this new aspect ratio, and we just use here just use only 2 images to generate, and we just call it haunted house. Image is generated. So let's take a look, and these are the 2 vertical images, and our target was haunted house, and that is what has been created. So we were able to cover all these 3 different models from ruDALL-E 1.3 billion parameter XL series. The notebook which we have just completed is available in this ruDALL-E folder at this DeepWorks GitHub repo. Along with Jupyter Notebook, some instructions and a lot more content is also available for you to review by yourself. So that's all I had for you in this tutorial. I hope you have enjoyed the content in my video. If you have liked it, please do share it. Please subscribe my channel and also comment your feedback or any suggestions you have. I do appreciate your time, and I'm looking forward to see you in my next video. Until then, please be good and do good. Thank you.